At this very moment, the Voyager 1 spacecraft is rushing through the void of interstellar space at a speed of 38,000 miles per hour. That sounds incredibly fast, does it not? However, here is the reality of the situation. Even moving at that tremendous velocity, it would still take Voyager 70,000 years just to arrive at the nearest star. Today, we are going to dive deep into the breathtaking reality of how fast we can truly travel through the cosmos using the technology we have right now. And believe me, when I say this, the answer is going to completely change how you view humanity's place within the universe. If you find yourself captivated by our journey through the cosmos and wish to uncover more mind-bending mysteries of space, please be sure to subscribe to this channel and leave a like. Now, let us begin. When we discuss the speed of space travel, we first need to comprehend that we are dealing with distances so vast they make the Earth look like a tiny grain of dust. The Moon, which is our closest celestial neighbor, is positioned roughly 238,900 miles away. The Apollo missions required 3 days to reach it, traveling at approximately 25,000 miles per hour during their trans-lunar injection. That is faster than any commercial jetliner and faster than any bullet ever fired. Yet, in cosmic terms, it is like crawling at a snail's pace. But here is where it gets truly interesting. The fastest object ever made by humans is not heading away from Earth. It is diving directly toward the Sun. The Parker Solar Probe, which was launched in the year 2018, has shattered every speed record we have ever established. As it swoops around our star, utilizing the gravity of Venus to tighten its orbit, it reaches staggering speeds of 430,000 miles per hour. That is fast enough to travel from New York to London in under 30 seconds. Yet, even at this blistering pace, it would still take over 6,000 years to reach Proxima Centauri, our nearest stellar neighbor. Let me paint you a picture to illustrate just how vast space really is. If the Earth were the size of a small marble, the Moon would be a pea sitting about 1 foot away. Mars, at its closest approach, would be a smaller marble, roughly 30 feet away. The Sun would be a beach ball located 400 feet away. And Proxima Centauri? It would be another beach ball located 24,000 miles away, which is the entire circumference of the Earth. These are not just numbers. They are a humbling reminder of the massive cathedral of emptiness that we call our home. The Voyager missions, launched in the year 1977, represent humanity's most distant ambassadors. Voyager 1 crossed into interstellar space in the year 2012, becoming the very first human-made object to leave the protective bubble of our solar system. It is now over 15 billion miles away from Earth. It is so far away that radio signals, traveling at the speed of light, take over 22 hours just to reach it. Think about that for a moment. A single conversation with Voyager involves waiting almost 2 days for a response. What makes the speed of Voyager even more remarkable is exactly how it achieved it. The spacecraft utilized a technique known as gravity assist, essentially stealing momentum from the giant planets. As Voyager 1 flew past Jupiter, it did not just passively drift by. It fell toward the planet, picking up immense speed, and then used that momentum to slingshot itself toward Saturn. Each planetary encounter added thousands of miles per hour to its velocity, acting like a cosmic pinball machine where every bounce makes you go faster. New Horizons, the probe which gave us those stunning images of Pluto in the year 2015, holds the record for the fastest launch ever from Earth. It departed our planet at 36,000 miles per hour, which is fast enough to pass the orbit of the Moon in just 9 hours. Apollo took 3 days to cover that very same distance. But here is the sobering part. Even with that incredible initial speed, it still took 9.5 years to reach Pluto. And Pluto is still within our solar system, our cosmic backyard. The physics of space travel fights against us at every single turn. There is no air to push against and no road to drive upon. Every bit of speed must come from throwing mass in the opposite direction, Newton's third law in its purest form. Chemical rockets, like those that powered the Saturn V, are essentially controlled explosions throwing hot gas out of the back. They are powerful, but they are inefficient. About 90% of a rocket's weight is fuel, and most of that fuel is used just to lift the rest of the fuel off the ground. Ion drives represent our attempt to be clever about propulsion. Instead of violent chemical explosions, they use electricity to accelerate charged particles to incredible speeds, up to 90,000 miles per hour. The exhaust velocity is 10 times higher than chemical rockets, meaning you need less fuel for the same change in speed. NASA's Dawn spacecraft used ion propulsion to visit both Vesta and Ceres, something that would be impossible with traditional rockets. But ion drives produce thrust so gentle that you could balance the force on a single sheet of paper. They are marathon runners, not sprinters. The fastest we have ever brought humans is during the Apollo 10 mission, when Tom Stafford, John Young, and Eugene Cernan hit 24,791 miles per hour relative to Earth during their return from the Moon. For a brief moment, they were the fastest humans in history, covering 7 miles every single second. Yet, if they had maintained that speed toward Proxima Centauri, their journey would take over 100,000 years. We would need to go 4,000 times faster just to make the trip in a single human lifetime. Solar sails offer a completely different approach. Instead of carrying fuel, they ride on sunlight itself. Photons from the sun have no mass, but they do carry momentum. And when they bounce off a reflective sail, they give a tiny push. It is like trying to move a battleship by throwing ping-pong balls at it. But in the vacuum of space, those tiny pushes add up. The Japanese Icaros mission proved this works, and the Planetary Society's light sail missions have demonstrated controlled solar sailing. But even our most ambitious solar sail concepts face harsh realities. The pressure from sunlight weakens with distance. By the time you reach Jupiter, it is 25 times weaker than at Earth. To reach high speeds, you would need enormous sails, possibly miles across, made of material thinner than tissue paper, yet strong enough not to tear. The engineering challenges are staggering, and even if we solved them, we are still talking about decades to reach the nearest stars. The Breakthrough Starshot project, announced in the year 2016 by Stephen Hawking and Yuri Milner, represents perhaps our most ambitious attempt to reach another star within a human lifetime. The concept is elegantly simple, yet technologically staggering. Use powerful Earth-based lasers to push tiny spacecraft equipped with light sails to 20% of the speed of light. At that velocity, these starships could reach Proxima Centauri in just 20 years. But here is the catch. Each probe would weigh only a few grams, and we would need to build the most powerful laser array ever conceived, requiring as much power as 100 nuclear power plants. Speaking of the speed of light and its implications for space travel, if you are curious about what would happen if we could actually achieve that ultimate cosmic speed limit, check out my video titled, "What If We Could Travel at Light Speed Today?", where I explore the mind-bending physics and paradoxes of relativistic travel. The link is in the description below. Now, back to our current reality. Nuclear propulsion represents our best near-term hope for dramatically faster space travel. Project Orion, conceived in the 1950s, proposed using nuclear explosions to push a spacecraft forward. Imagine riding the shockwave of atomic bombs detonating behind a massive pusher plate. It sounds like science fiction, but the physics is sound. Such a vessel could theoretically reach 3 to 5% of the speed of light, making a journey to Proxima Centauri possible in about 150 years. The project was abandoned due to nuclear test ban treaties and the obvious environmental concerns of launching thousands of nuclear weapons into space. NASA's current nuclear propulsion research focuses on more modest approaches. Nuclear thermal rockets heat propellant using a fission reactor, achieving exhaust velocities twice that of chemical rockets. Nuclear electric propulsion uses reactors to power ion drives, combining the efficiency of electric propulsion with the power density of nuclear energy. These technologies could cut the travel time to Mars from 9 months to 3 or 4 months. This is revolutionary for human exploration, but still painfully slow for interstellar dreams. The speed of our current spacecraft becomes even more humbling when you consider time dilation. Though at our achievable velocities, the effects are barely noticeable. The GPS satellites orbiting Earth at 8,700 miles per hour experience time dilation of about 38 microseconds per day relative to Earth's surface. It is measurable and must be corrected for GPS to work, but it is hardly the dramatic time-warping effects you would need to make interstellar travel feasible within a human lifetime. Let us talk about the Breakthrough Propulsion Physics Program, NASA's former program that investigated seemingly impossible propulsion concepts. They studied everything from manipulating inertia to creating warp drives. While the program did not produce any miraculous breakthroughs, it highlighted a crucial point. Our current understanding of physics might be incomplete. Just as 19th-century scientists could not conceive of nuclear power, we might be missing something fundamental that could revolutionize space travel. The Alcubierre drive, proposed in the year 1994, offers a tantalizing glimpse of what might be possible if we could manipulate space-time itself. Instead of moving through space, you would compress space in front of your spacecraft and expand it behind, surfing on a wave of warped space-time. The mathematics checks out within Einstein's general relativity, but you would need exotic matter with negative energy density, something that might not even exist. Even if it does, recent calculations suggest you would need more energy than exists in the entire observable universe. Fusion rockets represent a more realistic future technology. By fusing hydrogen into helium, the same process that powers the sun, we could achieve exhaust velocities of 3 to 5% of the speed of light. Project Daedalus, a study by the British Interplanetary Society in the 1970s, designed an unmanned probe that could reach Barnard's star in 50 years using fusion propulsion. The spacecraft would be enormous, assembled in orbit, and would require mining helium-3 from Jupiter's atmosphere. We are still decades away from sustained fusion power on Earth, let alone in a spacecraft. The EM drive controversy illustrates how desperate we are for propulsion breakthroughs. This device claimed to produce thrust without expelling any propellant, violating the conservation of momentum. Initial tests showed tiny amounts of thrust, sparking headlines about impossible space drives. But more careful experiments revealed the thrust was likely experimental error, thermal expansion, magnetic interactions, or other mundane effects. The episode reminds us that while we should remain open to revolutionary ideas, extraordinary claims require extraordinary evidence. Current ion drive technology continues to improve incrementally. NASA's Next-C ion thruster can operate continuously for over 5 years, achieving total velocity changes impossible with chemical rockets. The European Space Agency's Bepi-Colombo mission to Mercury uses 4 ion thrusters for its 7-year journey, slowly spiraling through the inner solar system. These patient spacecraft demonstrate that sometimes the tortoise really does beat the hare, at least within our solar system. The James Webb Space Telescope, positioned at the second Lagrange point nearly 1 million miles from Earth, showcases another aspect of space travel. Sometimes the best strategy is not to travel at all. By carefully balancing gravitational forces, spacecraft can hover at these cosmic parking spots with minimal fuel expenditure. It took Webb a month to reach its destination, traveling at a leisurely 2,000 miles per hour. But once there, it can maintain its position for decades with tiny adjustments. Plasma propulsion represents another promising technology. VSIMR, which stands for Variable Specific Impulse Magnetoplasma Rocket, uses radio waves to heat argon gas into plasma, then accelerates it with magnetic fields. It is like having a gear shift for your rocket, able to trade thrust for efficiency as needed. A Vasimer-powered spacecraft could reach Mars in 39 days compared to the 6 to 9 months required by chemical rockets. But it requires significant electrical power, likely from nuclear reactors, adding complexity and mass. The harsh truth is that our fastest spacecraft are still 10,000 times too slow for practical interstellar travel. If the distance to Proxima Centauri were reduced to 1 mile, our fastest probe would be crawling at about 5 feet per hour. A garden snail moves at about 3 feet per hour. So, we are barely outpacing snails on the cosmic scale. This is not a failure of engineering or imagination. It is a consequence of the universe's fundamental structure. But here is something that might surprise you. Sometimes going slower is actually faster in space. The Interplanetary Transport Network, discovered through computer simulations, reveals a hidden highway system throughout our solar system. By following these gravitational pathways, spacecraft can travel between planets and moons using almost no fuel, riding the subtle tides of competing gravitational fields. The trade-off is time. A journey that might take months with conventional rockets could take years via these cosmic currents, but you would arrive with your fuel tanks nearly full. The Japanese Hayabusa 2 mission exemplifies our current capabilities perfectly. Launched in the year 2014, it traveled for 3.5 years to reach the asteroid Ryugu, collected samples, and returned them to Earth in the year 2020. The entire journey covered over 3 billion miles at an average speed of about 30,000 miles per hour. This mission showcased ion propulsion, precision navigation, and sample return technology. Yet, it took 6 years to visit a rock in our own solar system. OSIRIS-REx tells a similar story. NASA's asteroid sample return mission launched in 2016, reached Bennu in 2018, and delivered its precious cargo to Earth in 2023. 7 years for a round trip to an asteroid that comes relatively close to Earth. These missions are not slow because of poor engineering. They represent the pinnacle of our current capabilities. The universe is just that vast, and physics is that unforgiving. Let us put our speed limitations in perspective with a thought experiment. Imagine you are on a spacecraft traveling at Voyager 1's current speed, 38,000 miles per hour. You decide to take a journey to every planet in our solar system, spending just 1 day at each destination. Your grand tour would take over 30 years, and that is just to visit our immediate cosmic family. The nearest star system would still be 70,000 years away. The Chinese Chang'e missions to the Moon demonstrate how we are getting better at space travel within our means. Chang'e 5 reached the Moon in just 4.5 days, collected samples and returned them to Earth, completing in weeks what took Apollo astronauts the same time for just the outbound journey. We are not necessarily going faster, but we are going smarter, using better trajectories and more efficient engines. Solar electric propulsion is quietly revolutionizing how we explore the solar system. The Psyche mission, launched in 2023, uses Hall-effect thrusters to journey to a metal asteroid. These thrusters are 10 times more efficient than chemical rockets, allowing missions previously thought impossible. But efficiency comes with patience. Psyche will not reach its destination until the year 2029, taking 6 years to cover what chemical rockets could do in 3, albeit using far more fuel. The challenge of space debris adds another layer to our speed conversation. In low Earth orbit, objects travel at 17,500 miles per hour. At these velocities, a paint fleck becomes a bullet and a loose screw becomes a cannonball. The International Space Station regularly adjusts its orbit to avoid debris, reminding us that sometimes in space, speed kills. Future spacecraft will need to balance the desire for velocity with the need for survival. Laser propulsion for larger spacecraft remains tantalizingly out of reach. While breakthrough Starshot envisions pushing gram-scale probes, scaling up to human-carrying vessels, would require laser arrays covering thousands of square miles and power generation exceeding global capacity. Even if we built such a system, the acceleration would be gradual, taking years to reach significant fractions of light speed while slowly cooking the spacecraft with waste heat from the lasers. The economics of speed in space are brutal. Every mile per hour of additional velocity requires fuel, and fuel requires more fuel to carry it. This tyranny of the rocket equation means that doubling your speed does not double your fuel needs. It might multiply them by 10 or more. SpaceX's Starship, despite its revolutionary reusability, still faces these same fundamental physics constraints. Even with perfect engineering, chemistry limits how fast we can throw atoms out the back of a rocket. Magnetic field propulsion concepts like the Bussard ramjet offer intriguing possibilities. The idea is elegant. Use massive magnetic fields to scoop up interstellar hydrogen, compress it to fusion conditions, and use it as both fuel and reaction mass. You would never run out of fuel, potentially allowing continuous acceleration, but the engineering challenges are staggering. The magnetic fields would need to extend thousands of miles, and the drag from collecting interstellar medium might exceed the thrust at achievable speeds. The Voyager golden records carry a poignant message about our speed limitations. These phonograph records attached to both Voyager spacecraft contain sounds and images of Earth. But they are not really meant for aliens. At Voyager's speed, it will not come within 1.6 light-years of another star for 40,000 years. They are more like messages in bottles thrown into an ocean so vast that no shore may ever be reached. They are monuments to human ambition constrained by cosmic reality. Europa Clipper, launched in 2024, showcases our current sweet spot for space exploration. Using gravity assists from Mars and Earth, it will reach Jupiter in the year 2030. The spacecraft will then perform nearly 50 flybys of Europa, Jupiter's ice-covered moon, searching for signs of habitability in its subsurface ocean. 6 years to reach Jupiter is faster than Galileo's 7 years in the 1990s, but still a testament to the distances involved. The problem with going faster is not just technological, it is energetic. To accelerate 1 kilogram to just 1% of light speed requires energy equivalent to a nuclear bomb. To reach 10%, you would need the energy output of a large power plant running for years. The universe seems to have a speed tax that increases exponentially, making each additional percentage point prohibitively expensive. We are not just fighting distance. We are fighting the fundamental relationship between energy and velocity. The Dawn mission changed how we think about visiting multiple destinations in space. Using ion propulsion, it became the first spacecraft to orbit 2 different bodies beyond Earth: the giant asteroid Vesta and the dwarf planet Ceres. Chemical rockets could never achieve this. They would run out of fuel after reaching the first target. Dawn's xenon-powered ion drive sipped fuel so efficiently it could spiral into orbit, study its target for months, then leave for another world. Total mission time: 11 years, but it accomplished what would have been impossible with traditional propulsion. Here is a reality check that might sting. If you started a journey to Proxima Centauri today at our current maximum speed, you would arrive in the year 78,000 AD. Human civilization as we know it is only about 10,000 years old. The journey would take 7 times longer than all of recorded human history. Your descendants aboard the ship would be as distant from you as we are from the first farmers. Language, culture, even human biology might evolve beyond recognition during the voyage. The Juno mission to Jupiter demonstrates another crucial aspect of space travel. Sometimes you have to go backward to go forward. To reach Jupiter efficiently, Juno first flew out past Mars's orbit, then fell back toward the Sun, using Earth's gravity for a speed boost. This cosmic billiard shot added over 7,000 miles per hour to its velocity. Without this assistance, the mission would have needed a much larger rocket or taken years longer. In space navigation, the shortest distance between 2 points is rarely a straight line. Let us talk about something called the Oberth effect, one of the few friends we have in the physics of space travel. When you fire your engines deep in a gravity well close to a planet or star, you get more bang for your buck. The same amount of fuel produces a greater change in orbit. It is like pushing a swing at the bottom of its arc versus the top. The Parker Solar Probe exploits this magnificently, firing its engines at perihelion when screaming past the Sun at maximum speed. The concept of specific impulse helps explain why different propulsion systems have such varied capabilities. Chemical rockets, for all their thunder and fury, have specific impulses around 450 seconds. Ion drives achieve 3,000 to 10,000 seconds. This number essentially tells you how efficiently an engine uses propellant. It is why ion drives can achieve much higher final velocities despite their whisper-gentle thrust. But even our best ion drives would take centuries to build up to speeds where interstellar travel becomes feasible. Space tethers represent one of the more exotic propulsion concepts actually tested in orbit. The idea is beautifully simple. Deploy a long conducting cable from a spacecraft in Earth's magnetic field. As it cuts through the field lines, it generates electricity which can be used to run ion thrusters or run current through the tether to push against the magnetic field for propulsion. It is like sailing on magnetic winds. Several tether experiments have flown with mixed results. The physics works, but keeping kilometer-long cables stable and intact proves challenging. The Bepi Colombo mission to Mercury showcases the choreography required for modern planetary exploration. Launched in 2018, it will not reach Mercury until 2025. 7 years for a planet that is only 48 million miles away at its closest approach. Why so long? The spacecraft must perform 1 flyby of Earth, 2 of Venus, and 6 of Mercury itself to bleed off enough velocity to enter orbit. Flying to Mercury is like trying to stop a ball rolling down a hill. The Sun's gravity wants to accelerate you, not slow you down. Here is something that might blow your mind about our current speed limits. The fastest human-made object relative to Earth is not heading out into space. It is a manhole cover. During a 1957 nuclear test, a heavy steel cap was blasted off a vertical shaft. High-speed cameras caught it moving at over 125,000 miles per hour. If it survived the atmospheric heating, it might have become Earth's first accidental space probe. But even at that incredible speed, it would still take over 20,000 years to reach the nearest star. The Dragonfly mission to Saturn's moon Titan represents a new approach to exploration speed. Rather than racing to get there quickly, it is designed to explore quickly once it arrives. This nuclear-powered drone will hop across Titan's surface, covering more ground in a single flight than Mars rovers traverse in years. It reaches Titan in 2034, but then conducts years of aerial exploration. Sometimes the real speed that matters is not how fast you travel between worlds, but how efficiently you explore once you arrive. Let me share a sobering comparison. Light, the ultimate speed limit, crosses the diameter of Earth's orbit in about 16 minutes. Our fastest spacecraft would take months to cover the same distance. If light speed is a Formula One race car doing 200 miles per hour, our best spacecraft are bicycles pedaling at about 1/10 of a mile per hour. We are not just slow. We are cosmically, fundamentally, almost impossibly slow relative to the scale of space. The Rosetta mission's decade-long journey to Comet 67P illustrates the patience required for deep space exploration. Launched in 2004, it performed gravity assists at Earth 3 times and Mars once, building up enough velocity to match orbits with a comet racing around the Sun. 10 years of travel for a few years of science. But those years revolutionized our understanding of comets. In space exploration, patience is not just a virtue, it is a necessity. Nuclear pulse propulsion keeps returning to serious scientific discussion because the physics is so compelling. Project Daedalus envisioned fusion pellets detonating, behind a spacecraft 50 times per second, each explosion pushing against a massive plate. Theoretical velocities reached 12% of light speed, but we are talking about a spacecraft weighing 50,000 tons assembled in orbit using technology we have not invented yet. It is a reminder that even our most ambitious concepts would take centuries to reach the stars. The Mars Sample Return mission, planned for the 2030s, highlights our current capabilities perfectly. It will take about 2 years to get samples from Mars back to Earth. And that is with multiple spacecraft working in relay. One to collect samples, one to launch them from Mars, one to catch them in orbit, and one to bring them home. This Rube Goldberg complexity is necessary because we simply cannot build a single rocket powerful enough to make the round trip. Speed in space often means accepting complexity. The Breakthrough Propulsion Physics program that NASA ran from 1996 to 2002 investigated some truly wild ideas. They studied whether the quantum vacuum could be pushed against for propulsion, whether inertia could be modified, and whether faster-than-light travel might be possible through wormholes or warp drives. The program did not produce any breakthroughs, but it highlighted something important. We are so constrained by current physics that we are willing to investigate seemingly impossible ideas just in case our understanding is incomplete. Consider the energetics of our situation. The Saturn V rocket, the most powerful vehicle ever built, burned through its fuel in just 17 minutes of total engine time. Those 17 minutes were enough to send Apollo to the moon. But to reach even 1% of light speed, you would need to burn similar engines continuously for years. The energy requirements do not scale linearly. They explode exponentially. We are not just fighting distance. We are fighting the fundamental mathematics of kinetic energy. The LISA Pathfinder mission demonstrated technology that seems almost magical. The ability to shield a test mass so perfectly from all forces that it floats in true gravitational freefall. This technology will enable LISA, the space-based gravitational wave detector, to measure ripples in space-time itself. But here is the thing. Even detecting waves that travel at light speed does not help us travel faster. We can measure the ultimate cosmic speed limit with exquisite precision, but we cannot approach it. Let us talk about something called the weight calculation. Given exponential technological advancement, when should you launch an interstellar mission? Launch too early with primitive technology, and a faster ship launched decades later will pass you. Launch too late, and you have wasted time waiting for our current technology. The calculation is brutal. Unless we are confident we can improve propulsion by factors of thousands, it is better to wait. We are so slow that future generations will almost certainly pass any mission we launch today. The Starshot project faces challenges beyond just building powerful lasers. At 20% of light speed, hitting a dust grain would be like a nuclear explosion. The probe needs to survive 20 years of interstellar bombardment. It needs to aim itself precisely enough to fly past Proxima Centauri at useful distances. It needs to transmit data back across 4 light-years with a transmitter powered by whatever energy it can harvest. Each challenge alone is daunting. Together, they push the boundaries of what physics allows. Here is a perspective shift that might help. The pale blue dot photograph, taken by Voyager 1 from 6 billion kilometers away, shows Earth as a tiny speck in a sunbeam. At that distance, radio signals take 5.5 hours each way. A conversation involves 11-hour gaps. Now, imagine controlling a probe at Proxima Centauri, where signals take 4 years each way. An 8-year round trip for each command and response. At our current speeds, robotic exploration is the only option, and even that requires patience measured in decades. The Genesis mission returned solar wind samples to Earth using a technology that seems almost primitive: parachutes. But the mission showcases a crucial point about space exploration. Sometimes the cleverest approach is not going faster, but being smarter about what you are trying to achieve. Genesis collected particles from the Sun without traveling to the Sun, catching them as they streamed past Earth. In space exploration, wisdom often trumps speed. Magnetic sails represent another approach to propulsion that works with rather than against the space environment. Instead of pushing against nothing, they push against the solar wind, the stream of charged particles flowing from the Sun. Deploy a magnetic field around your spacecraft, and the solar wind pushes you like wind on a sailing ship. The acceleration is tiny but constant, and it requires no fuel, just electrical power. Several small-scale demonstrations have proven the concept, but scaling up remains challenging. The Spitzer Space Telescope operated for 16 years in an Earth-trailing orbit, slowly drifting away from our planet at about 0.1 astronomical units per year. That is a leisurely 10 million miles annually, barely a crawl by cosmic standards. Yet, this slow drift was perfect for its mission, keeping it away from Earth's heat while maintaining communication. Sometimes in space, the right speed is not the fastest speed. It is the speed that lets you accomplish your goals. Let me give you a reality check about chemical rockets, our workhorses of space exploration. The theoretical maximum exhaust velocity for chemical propulsion is about 4.5 kilometers per second, achieved by burning hydrogen with oxygen. We are already at 90% of that theoretical maximum. There is no breakthrough coming in chemical rockets. We have essentially maxed out what chemistry allows. To go significantly faster, we need to abandon chemistry altogether. The Cassini mission's grand finale demonstrates how we use gravity and geometry when we cannot use speed. In its final year, Cassini dove between Saturn and its rings 22 times, using the planet's gravity to reshape its orbit repeatedly. Each pass revealed new science, and the mission ended with a deliberate plunge into Saturn's atmosphere. We could not explore this region any other way. It required precise orbital mechanics, not raw speed. Solar gravitational lensing missions represent the ultimate in patient exploration. By positioning a telescope at 550 astronomical units from the Sun beyond Pluto, we could use our star's gravity as a massive lens capable of imaging exoplanets in extraordinary detail. But reaching that distance would take decades with current propulsion. The mission would be a gift to future generations, launched by people who would not live to see the results. The truth about antimatter propulsion is both exciting and disappointing. Yes, antimatter is the most efficient fuel possible, converting 100% of mass to energy. But we have produced only nanograms of antimatter in all of human history at costs of trillions of dollars per gram. Even if we could produce it efficiently, storing it requires perfect magnetic confinement. One power failure, and your fuel annihilates your spacecraft. It is the ultimate example of a technology that works perfectly in equations but fails catastrophically in engineering. The interstellar probe mission concept studied by NASA aims to reach 1,000 astronomical units from the Sun within 50 years of launch. That is about 4 times farther than Voyager 1 has traveled in 47 years. The proposed spacecraft would use a massive solar Oberth maneuver, diving close to the Sun before firing its engines at perihelion. Even this ambitious mission would only reach 0.016 light-years in 50 years, just 0.4% of the distance to Proxima Centauri. Here is something that puts our speed challenge in brutal perspective. If the entire Milky Way galaxy were shrunk down to the size of the United States, our fastest spacecraft would be moving at about 0.02 inches per year. At that scale, light itself would only travel at about 2 inches per second. The universe has not just made interstellar travel difficult. It has made it absurdly, almost mockingly difficult given the scales involved. The DART mission, which successfully altered an asteroid's orbit in 2022, demonstrates a different kind of speed. The speed of human ingenuity. We cannot travel fast, but we can think fast, plan precisely, and execute complex missions across vast distances. DART traveled for 10 months to hit a target just 160 meters across, millions of miles away. It is not about raw velocity. It is about precision calculation and the ability to project human influence across the solar system. Let us discuss the elephant in the room: generational ships. If we cannot go fast, could we go long? A spacecraft carrying thousands of people on a journey lasting centuries or millennia. The physics works, but the engineering is staggering. You would need a closed ecosystem reliable for centuries. You would need to maintain technology across generations. You would need to ensure the descendants of your crew still want to complete a mission their ancestors started. And at our current speeds, we are talking about journeys lasting thousands of generations. The Oort cloud, the sphere of icy bodies surrounding our solar system, extends perhaps halfway to the nearest star. Just reaching the inner edge would take Voyager 300 years. Crossing the entire cloud would take 30,000 years. This is not interstellar space. This is still our sun's gravitational backyard. The universe has placed moats around every star system, vast voids that mock our ambitions of stellar travel. Fusion ramjets represent perhaps our most realistic path to high-speed interstellar travel. But realistic is relative. The concept involves scooping interstellar hydrogen, compressing it to fusion conditions, and using the energy for propulsion. You would never run out of fuel, potentially allowing constant acceleration. But the engineering challenges are monumental. The scoop would need to be thousands of kilometers across. The fusion reactor would need to operate continuously for centuries. We cannot even build a fusion power plant on Earth yet. The Parker Solar Probe's heat shield showcases another limitation of going fast: thermal management. At just 0.06% of light speed, the probe needs a shield that can withstand 2,500 degrees Fahrenheit. The heating comes not from friction. Space is too empty for that, but from the compression of solar wind particles. At higher speeds, this heating becomes catastrophic. At 1% of light speed, interstellar hydrogen hits like radiation from a nuclear reactor. Speed does not just require energy, it requires surviving the consequences of that speed. Here is a thought experiment that illustrates our predicament. Imagine you are on a spacecraft that can magically accelerate at 1 g, Earth's gravity, continuously. You would reach Mars in 2 days, Jupiter in a week, Pluto in 3 weeks. You would be approaching light speed within a year. But maintaining that acceleration for a year would require more energy than humanity has produced in its entire history. And that is for a magical drive that is 100% efficient. Real rockets are lucky to achieve 1% efficiency. The Voyager spacecraft carry plutonium-238 radioisotope thermoelectric generators, nuclear batteries that convert radioactive decay into electricity. After 47 years, they are producing only about half their original power. By 2025, we will have to shut down most instruments to conserve energy. This highlights another challenge of long-duration space travel. Power systems degrade. Solar panels degrade, nuclear reactors run out of fuel. The universe does not just make space travel slow. It makes maintaining systems over the required timescales nearly impossible. Let me share something about the communications challenge that really drives home our limitations. When New Horizons flew past Pluto, it took 16 months to transmit all the data back to Earth. Not because of distance, though that added 5 hours of light lag, but because of power limitations. The spacecraft could only transmit at about 1 kilobit per second from Pluto's distance. Now, imagine trying to send data from Proxima Centauri 3,000 times farther away. The signal strength drops with the square of distance. Communication itself becomes nearly impossible. The SLS, Space Launch System, represents the current pinnacle of chemical rocket technology. It can put 95 tons into low Earth orbit, slightly less than the Saturn V from 50 years ago. Despite half a century of advancement, we have not dramatically improved our launch capabilities. Why? Because we are pushing against fundamental limits. Chemical bonds only contain so much energy. Rocket nozzles can only withstand so much heat and pressure. Materials can only be so strong and light. We are not failing to advance. We are approaching the ceiling of what is possible. The concept of laser highways has been proposed for interstellar travel. Instead of carrying fuel, spacecraft would ride on beams of laser light projected from stations throughout the solar system. Each station would accelerate passing spacecraft a bit more, like a cosmic railroad. But the infrastructure would be civilization scale. Thousands of laser stations, each requiring gigawatts of power, all perfectly coordinated. It is technically possible, but economically and politically implausible for the foreseeable future. The Kepler Space Telescope discovered thousands of exoplanets by staring at one patch of sky for years, watching for the tiny dimming as planets cross their stars. This patient observation revealed something profound. Planetary systems are common, but reaching them remains impossibly difficult. We can detect a planet thousands of light years away more easily than we can travel to the edge of our own solar system. Our eyes can see what our bodies can never reach. Here is a sobering fact about reaction mass. Every rocket, no matter how advanced, must throw something backward to move forward. Even if you had perfect efficiency and infinite energy, you still need mass to expel. For a journey to Proxima Centauri at 10% light speed, you would need to carry reaction mass equal to many times your spacecraft's weight. And that calculation assumes perfect efficiency. Real rockets might need mass ratios of thousands or millions to one. The rocket equation is not just inconvenient, it is tyrannical. The 30-meter telescope and other ground-based observatories represent a different approach to exploring the universe. Instead of going to the stars, we bring the stars to us through ever more powerful instruments. We can analyze the atmospheres of exoplanets, map the surfaces of asteroids, and peer into stellar nurseries, all from Earth. It is a reminder that exploration does not always require transportation. Sometimes the fastest way to explore the universe is to stay put and look harder. Let us talk about the psychological challenges of current space travel speeds. A journey to Mars takes 6 to 9 months each way. That is over a year in a tin can for a round trip. Astronauts on the ISS, just 250 miles up, experience psychological stress from confinement and isolation. Now imagine a journey to Proxima Centauri taking thousands of years. The human psyche did not evolve for such timescales. We are not just fighting physics, we are fighting our own nature. The Stardust mission collected comet dust and returned it to Earth. But here's the clever part. It did not chase down the comet at its full speed. Instead, it positioned itself in the comet's path and let the comet come to it, like a fielder positioning themselves to catch a baseball. The relative velocity was still 40,000 miles per hour, requiring an aerogel collector to gently capture the particles. Sometimes in space, being smart about positioning beats being fast. Nuclear electric propulsion represents our best near-term hope for faster deep space travel. A nuclear reactor generates electricity, which powers ion thrusters for years or decades. The Dawn mission proved ion propulsion works. Nuclear submarines prove we can operate reactors for decades. Combining them seems obvious, but the politics of launching nuclear reactors is complex, and the engineering of space-rated nuclear systems is challenging. We have the pieces, but struggle to put them together. The Lorentz force turns any charged particle moving through a magnetic field into a tiny spacecraft experiencing thrust. Some propulsion concepts use this principle. Accelerate plasma through magnetic fields for thrust. The problem? Creating strong enough magnetic fields requires superconducting magnets which need cooling to near absolute zero. In the cold of space, that is easier than on Earth. But maintaining superconductors for decades of travel adds another layer of complexity to already complex systems. Here is something wild. We have accidentally created the fastest human-made objects through nuclear testing. During underground tests, metal plates were sometimes launched at over 100,000 miles per hour. These accidental projectiles, if they survived atmospheric passage, would be our fastest spacecraft. It is a reminder that we can achieve incredible speeds, just not in controlled, useful ways. The universe allows speed but makes harnessing it for purposeful travel extraordinarily difficult. The Lunar Gateway Station represents a new philosophy in space exploration. Instead of racing to destinations, we are building infrastructure, waypoints that future missions can use. It is an acknowledgement that space exploration is a multi-generational project. We are not trying to reach the stars ourselves. We are laying foundations for our descendants. This patient approach might be frustrating for those who dream of Star Trek, but it is honest about our limitations. Time dilation offers false hope for interstellar travel. Yes, at 99% light speed, time passes 7 times slower for travelers. A journey to Proxima Centauri would take just 7 months ship time. But reaching such speeds requires impossible energies, and everyone you know on Earth would age 4 years while you experience 7 months. Even if we could achieve such speeds, we would be creating one-way trips to the future, not practical transportation. The Bussard-Ramjet concept fails for a heartbreaking reason. Yes, you could scoop interstellar hydrogen for fuel, but the drag from collecting it exceeds the thrust you generate until you are already traveling at a significant fraction of light speed. You need to be going fast to go faster, a cosmic catch-22, like needing experience to get a job that gives you experience. The universe seems to delight in these cruel ironies. Project Longshot, a 1980s design study, proposed an unmanned probe to Alpha Centauri powered by nuclear pulse propulsion. Journey time: 100 years. The probe would be assembled at a space station, fueled with helium-3 mined from Jupiter, and would mass 400 tons. Even this ambitious design would only achieve 5% light speed and would arrive with no way to slow down, making it a very expensive flyby mission lasting longer than any human institution has existed. The reality of space navigation adds another layer of difficulty. At interstellar distances, even tiny navigation errors compound into missing your target by millions of miles. Stars move relative to each other. Proxima Centauri will not be where it is now by the time a slow spacecraft arrives. You are not aiming where the star is, but where it will be, accounting for its motion and yours across centuries. One calculation error, and your 1,000-year journey ends in empty space. The Orion spacecraft, NASA's current crew vehicle, not the nuclear pulse concept, represents our honest capabilities for human spaceflight. It can support 4 astronauts for 21 days, maybe stretched to 6 months with additional supplies. That is enough for lunar missions, barely enough for Mars. Anything beyond Mars is fantasy with current life support technology. We are not just slow, we are fragile, requiring constant resupply of air, water, food, and power. Speed is meaningless if the crew dies en route. Here is a perspective that might change how you see our situation. The universe is expanding, and that expansion is accelerating. Galaxies beyond a certain distance are already unreachable. They are receding faster than light. Every second, more of the universe crosses this cosmic event horizon, becoming forever inaccessible. We are not just racing against the vast distances. We are racing against the universe itself, and we are losing. The observable universe is shrinking, and our slow speeds mean we are trapped in an ever smaller bubble of potential exploration. The EM Drive saga teaches us about the danger of wishful thinking in propulsion physics. This device claimed to produce thrust without expelling reaction mass, violating conservation of momentum. Teams worldwide tested it, some claiming positive results. But more careful experiments revealed the truth. The thrust was experimental error. interactions with Earth's magnetic field, or thermal effects. We wanted it to work so badly that we almost fooled ourselves. The universe does not care about our desires. Let us examine solar sails more closely. The Planetary Society's light sail missions proved the concept works, but the numbers are humbling. Light Sail 2, with a sail area of 32 square meters, experiences a push equivalent to the weight of a paperclip. To reach even 1% light speed would require sails kilometers across, made of material thinner than anything we can currently manufacture in such sizes. And solar pressure drops with distance squared. By Jupiter's orbit, it is 25 times weaker than at Earth. The Arecibo message, broadcast toward the globular cluster M13 in 1974, illustrates the futility of current-speed interstellar communication. The message will take 25,000 years to arrive. If anyone responds immediately, we will get an answer in the year 50,000 AD. By then, humans might have evolved into something unrecognizable or be extinct. We are not having conversations with the cosmos. We are leaving notes for species that do not yet exist. Gravitational assists, the technique of stealing momentum from planets, saved the Voyager missions. Without Jupiter's gravity, they would never have reached the outer planets within useful time frames. But here is the limit. You can only steal momentum a planet has to give. Even if you perfectly utilized every planet in our solar system, you would gain maybe 60 kilometers per second. That sounds impressive until you realize it is just 0.02% of light speed. The universe provides tools, but they are woefully inadequate for interstellar ambitions. The Mars helicopter Ingenuity demonstrates innovation within our speed constraints. It does not travel fast. Its top speed is about 20 miles per hour. But it revolutionized how we explore other worlds. Sometimes the breakthrough is not about going faster, but about finding new ways to explore at the speeds we can achieve. Ingenuity has shown that aerial exploration of Mars is possible, opening new dimensions for future missions. Here is the cruel mathematics of the rocket equation. To accelerate a 1-ton payload to just 1% light speed using perfect hydrogen-oxygen rockets would require 10 to the power of 1,400 tons of fuel. That is a number so large it has no physical meaning. It exceeds the number of atoms in the observable universe. The equation does not just make interstellar travel difficult. It makes it mathematically absurd with chemical propulsion. The concept of generation ships assumes we can maintain a closed ecosystem for centuries. But Biosphere 2, our best attempt at a closed ecosystem on Earth, failed within 2 years. Oxygen levels dropped, carbon dioxide spiked, species went extinct. The concrete absorbed atmospheric gases in unexpected ways. And this was on Earth, where we could intervene when things went wrong. A generation ship would have no such safety net, carrying all of humanity's eggs in one very fragile basket, traveling at cosmic crawling speed. Metamaterials offer tantalizing possibilities for exotic propulsion. These engineered structures have properties not found in nature: negative refractive indices, acoustic cloaking, and more. Some theorists speculate about space-time metamaterials that could reduce effective mass or create propulsion without reaction mass. But we can barely manufacture these materials in laboratory quantities for simple applications. Scaling to spacecraft propulsion remains deep in the realm of speculation. The Fermi paradox gains new meaning when you understand our speed limitations. Maybe the universe is full of intelligent life, but they are all trapped in their own star systems by the same physics that traps us. The Great Filter might simply be the speed of light. Civilizations rise, look at the stars, calculate the requirements for interstellar travel, and resign themselves to isolation. The universe might be full of intelligence, each species alone on their island, separated by oceans of space-time no one can cross. Communication with Voyager demonstrates the challenge of maintaining contact over interstellar distances. The spacecraft transmits with 23 watts, about the power of a refrigerator light bulb. NASA needs 70-meter dishes to hear its whisper from 15 billion miles away. At Proxima Centauri's distance, that whisper would be 10,000 times fainter. We would need receivers kilometers across to detect signals from our nearest stellar neighbor. Even communication faces the tyranny of distance. The focal mission concept would use the Sun's gravity as a telescope lens capable of imaging exoplanets in extraordinary detail. But the focal point is 550 astronomical units away, far beyond Pluto. Reaching it would take decades with current propulsion. The mission would be a gift to future generations, launched by people who would not live to see the results. It perfectly encapsulates our situation. We can conceive of incredible science, but the travel times exceed human lifespans. The truth about warp drives is both fascinating and frustrating. Yes, general relativity allows for space-time geometries that could transport you faster than light without locally exceeding light speed. The Alcubierre metric is mathematically valid, but it requires exotic matter with negative energy density, something that might not exist. Even if it does, you would need planet-sized masses of it. And recent calculations suggest creating a warp bubble might require more energy than exists in the observable universe. Physics allows it in principle but forbids it in practice. Let us put our current speeds in a historical context. In 1869, the Cutty Sark could sail from London to Sydney in about 80 days. Today, we fly it in 24 hours, roughly 80 times faster. If we achieved similar improvement in space travel, we would be approaching 1% light speed. But we have not. Despite a century of rocketry, we are only about 10 times faster than our earlier spacecraft. The curve of progress has flattened against the wall of physics. The Perseverance rover's journey to Mars illustrates our current reality perfectly. Launched in July of 2020, it arrived in February of 2021. 7 months for a journey of about 300 million miles. The rover itself travels at a blistering 0.1 miles per hour on Mars's surface. We have sent a nuclear-powered robot to another planet, and it moves slower than a garden snail. That is not a failure of engineering. It is an acknowledgement of the energy costs of movement on another world. Here is something that keeps propulsion physicists up at night. Even if we discovered some exotic new physics, negative mass, wormholes, whatever, we would still face the engineering challenge of building devices that exploit these phenomena. It took 40 years from Einstein's E equals mc squared to the first nuclear reactor. How long from discovering faster-than-light physics to building a faster-than-light drive? Centuries? Millennia? The universe might allow shortcuts we have not discovered, but building the on-ramps could take longer than civilizations last. The asteroid belt represents both opportunity and frustration for space travel. It contains enough raw materials to build thousands of spacecraft, but reaching and mining those asteroids requires the very propulsion systems we would be trying to build. It is like having all the ingredients for a cake locked in a box that requires a cake to open. The universe's resources are there, but accessing them requires capabilities we are trying to develop. Magnetic reconnection in space plasmas offers a glimpse of natural particle acceleration. During solar flares, magnetic field lines snap and reconnect, accelerating particles to near light speed in seconds. Nature achieves casually what we struggle to accomplish with billion-dollar accelerators. But harnessing these phenomena for propulsion remains beyond us. We can observe the universe's particle accelerators, but we cannot build them. The concept of relativistic rockets highlights a cruel irony. As you approach light speed, your rocket exhaust becomes less effective at pushing you forward. The faster you go, the less thrust you get from the same exhaust velocity. It is like trying to run up an escalator that speeds up the faster you climb. The universe does not just set a speed limit. It actively resists your attempts to approach it. Let us talk about the most ambitious propulsion concept ever seriously studied: Project Daedalus. This unmanned probe would use deuterium-helium-3 fusion, achieve 12% light speed, and reach Barnard's star in 50 years. The design called for a spacecraft weighing 54,000 tons assembled in orbit, fueled by helium-3 mined from Jupiter's atmosphere. Even this monument to human ambition would be a one-way flyby mission, unable to slow down at its destination. The cosmic microwave background provides a universal reference frame for measuring our true speed through space. Earth moves at about 370 kilometers per second relative to this background. Already 0.1% of light speed just from our galaxy's motion through space. We are already cosmic speed demons by human standards, but it is still 10,000 times too slow for interstellar travel. The universe has given us a head start that does not help at all. Here is a reality check about artificial intelligence and space exploration. Some suggest sending AI probes instead of humans, avoiding life support constraints. But even AI probes face the same propulsion limits. They might tolerate higher accelerations and longer journeys, but they still need energy to accelerate and reaction mass to expel. The universe does not care if the pilot is biological or digital. Physics applies equally to all. The concept of Shkadov thrusters, stellar engines that move entire stars, represents the ultimate in thinking big. By building a partial Dyson sphere that reflects a star's light asymmetrically, you could slowly push the star and its planets in a chosen direction. Travel speed? About 50 kilometers per second after a million years of acceleration. Even commandeering the power of an entire star gives you just 0.017% of light speed. The universe laughs at even our most audacious schemes. Breakthrough. Listen, the search for extraterrestrial intelligence has detected no convincing signals despite surveying millions of stars. Maybe that is because broadcasting across interstellar distances requires enormous power, and civilizations realize it is futile. At our current speeds, physical contact is impossible, and even communication involves decade-long delays. Perhaps the universe is full of civilizations that have all reached the same conclusion. We are stuck where we are. The Parker Solar Probe's heat shield is made of carbon composite foam 4.5 inches thick. At just 430,000 miles per hour, which is 0.06% light speed, it needs this protection from the solar environment. The heating scales with velocity cubed for atmospheric entry. At 1% light speed, no material could survive. At 10%, atoms themselves would be stripped apart by the impact energy. Speed kills, literally. The truth about our current space travel capabilities is both humbling and inspiring. We have achieved what our ancestors would have called magic, sending robots to other worlds, humans to the moon, probes beyond our solar system. Yet, we have barely scratched the surface of what is possible in the universe. The fastest we can currently travel is about 0.06% of light speed with the Parker Solar Probe, and that is a brief sprint near the Sun, not sustainable for interstellar journeys. Let us bring this full circle with a thought that might shift your perspective. The atoms in your body were forged in stars that exploded billions of years ago. Those atoms traveled through interstellar space for eons before coalescing into the solar system, Earth, and eventually you. In a very real sense, you have already made the ultimate journey from stellar cores across light years to this moment. The stardust that forms you traveled at cosmic speeds we can only dream of achieving with our spacecraft. The Hubble Space Telescope orbits at just 17,000 miles per hour, crawling by cosmic standards. Yet, it has revolutionized our understanding of the universe, revealing galaxies billions of light-years away, measuring the universe's expansion, detecting exoplanet atmospheres. Sometimes the speed that matters is not how fast you travel, but how far you can see. Hubble reminds us that exploration is not only about going there, it is about understanding from here. The Mars rover's Spirit, Opportunity, curiosity, and perseverance have collectively traveled less than 100 meters across the Martian surface in decades of exploration. Their top speed would not outpace a leisurely stroll. Yet, they have transformed our understanding of Mars, finding evidence of ancient water, analyzing rock chemistry, and paving the way for future human exploration. Slow and steady is not just winning the race. It is the only race we can currently run. Here is a final perspective on interstellar travel. If we launched a mission to Proxima Centauri today at our maximum achievable speed, it would arrive in about 70,000 years. By comparison, anatomically modern humans emerged only about 300,000 years ago. We have been practicing agriculture for 10,000 years, had written language for 5,000 years, and had electricity for only about 150 years. The journey would take longer than our entire technological civilization has existed. But maybe that is okay. Maybe the journey is supposed to be multi-generational, not just for the travelers, but for the entire species. We plant trees whose shade we will never sit under. We build cathedrals we will never see completed. Perhaps space exploration is humanity's ultimate cathedral, a project that spans not just lifetimes but entire epochs of civilization. The JWST, James Webb Space Telescope, sits at a gravitationally stable point 1 million miles from Earth, traveling at the same speed Earth orbits the Sun. It is not rushing anywhere, but it is peering deeper into space and time than any instrument before it. It sees galaxies as they were 13 billion years ago, watching the universe's childhood unfold. Speed through space matters less when you can travel through time with light. Current propulsion technology limits us to our solar system for practical purposes. The outer planets are within reach, difficult, requiring years of travel, but achievable. The Kuiper Belt and Oort cloud stretch the boundaries of what is possible. Beyond that, we are in the realm of theoretical missions that would outlast nations and maybe species. This is not pessimism. It is an honest assessment of where we stand. But here is what fills me with wonder. Despite these limitations, we have still reached beyond our world. 12 humans have walked on the moon. Rovers explore Mars as I speak. Probes have visited every planet in our solar system. We have landed on asteroids, comets, and Saturn's moon, Titan. We have sent spacecraft into interstellar space. We are slow, yes, but we are moving. The future of space travel might not be about going faster, but about going smarter. Self-replicating probes that build copies of themselves from asteroid materials. Solar sails that accelerate for decades, reaching speeds impossible for rockets. Laser propulsion networks that push spacecraft without carrying fuel. Nuclear fusion drives when we finally master fusion. Each advance will not be revolutionary but incremental, slowly expanding our cosmic reach. Here is my hope, that we are in the equivalent of the maritime age, when crossing oceans took months and was incredibly dangerous. Eventually, we developed faster ships than steam power, then aircraft. Perhaps in centuries to come, our descendants will look back at our chemical rockets with the same affectionate nostalgia we feel for sailing ships. They will marvel that we reached the moon with such primitive technology. The Voyager. Golden records will outlast human civilization. Even after Earth is gone, those phonograph records will still be sailing through interstellar space, carrying sounds and images of a species that dared to reach beyond its world. Our current speeds are slow, but our ambitions are eternal, literally. We are not just exploring space. We are announcing our existence to the universe. So, how fast can we travel in space right now? The answer is, very slowly by cosmic standards, but faster than any previous generation and fast enough to have visited every planet in our solar system. We are toddlers taking our first steps into a vast universe. And we are doing it with the grace and clumsiness that beginners always show, but we are learning, adapting, and pushing forward. Every mission teaches us something new. Every failure informs the next attempt. The Parker Solar Probe's heat shield technologies will enable closer solar study. Ion drive experience from Dawn and Bepi Colombo will improve future designs. Each gravity assist we perform refines our understanding of orbital mechanics. We are not just exploring space. We are building the knowledge foundation that future generations will use to go farther and faster. Remember, it took life on Earth 3.5 billion years to produce a species capable of leaving the planet. We have been spacefaring for only 67 years, 6 billionths of that time. We are incredibly young at this. The universe is 13.8 billion years old, and we are newborns by comparison. Perhaps our current speed limitations are not failures, but growing pains. The cosmic speed limit might seem like a prison, but it is also a teacher. It forces us to be patient, thoughtful, and clever. It demands we solve problems with intelligence rather than brute force. It makes us treasure every mission, every data point, every image sent back from distant worlds. If space travel were easy, would it inspire the same sense of wonder? Thank you for joining me on this exploration of humanity's current capabilities in space. We are slow, yes, but we are moving. We are limited, yes, but we are learning. We are stuck in our cosmic neighborhood for now, but we are looking outward with instruments that can see to the edge of the observable universe. If this journey through our current speeds has given you a new appreciation for both our limitations and our potential, please share this video with someone who dreams of the stars. Subscribe to continue exploring the greatest questions about our universe. And remember, you are made of atoms that have already traveled across the cosmos. You are not separate from the universe. You are how the universe explores itself. We might be moving slowly through space, but we are moving quickly through understanding. And sometimes that is the speed that matters most. What other cosmic mysteries should we explore together? Leave your suggestions in the comments below. Until next time, keep looking up, keep asking questions, and never forget that we are all crew members on Spaceship Earth, traveling through the cosmos at speeds our ancestors could not have imagined. We are already space travelers. We are just learning to be better ones. If you are still watching, make sure to subscribe to the channel and give a thumbs up. And if you want to keep exploring the mysteries of the universe, I am sure you will love this other video on the left side of the screen. This is why we cannot travel at light speed. Learn about the mind-bending effects of near-light-speed travel, the energy requirements that skyrocket toward infinity, and the quantum and thermodynamic barriers that make light speed unreachable, and much more. See you there.